Okay, I guess let's get started. So I think last week I spent some time reading the feedback from the survey. I've been go through all of them. So I guess I'm not going to discuss every points there. All the points are well taken, and thanks for all the very helpful feedback. And for some of those, I'm going to improve. I guess there are also some other conflictory requests, which still are very understandable because different people have different preferences. That's completely fine. But I guess I'm just saying that it's not like I can address all the possible requests, just because sometimes there are some constraints. But of course, sometimes I think even conflictory requests can be addressed if you are creative. I will try to do that as well. I guess I guess there's one thing I want to discuss a little bit, which I think might be useful for you. Is not trying to find any excuses for the lecture, but I think some people mentioned that it's a little bit hard to follow the take notes while listening to a lecture. I can completely understand that. I wrote pretty fast, which I'm going to slow down a little bit, at least to make the layout and the format a bit cleaner, easier to read. But I think, in my opinion, this, of course, I'm not saying that you have to really follow my way to take courses. I typically don't take a lot of notes. I think at least this course, I try to design so that you don't have to take all the notes yourself, just because we're going to have scrap notes later, and some of the scrap notes are already there. And when I listen to a theoretical lecture, I try to think more so that I can remember them in my head a little bit. Because I feel that, at least for me, it takes too much energy for taking all the notes. I'm not sure whether this is useful for everyone. I don't think it can be useful for everyone, but maybe you can try it a little bit just to see whether it's easier if you take a bit less notes and try to remember a little more. Anyways, I'm going to slow down a little bit, at least in terms of the writing for sure, and also probably I'm going to kind of slow down a little bit in terms of the overall pace a little bit as well, given some of the feedbacks saying that some of the lectures are a little bit too fast. And also another thing is that I think the homework questions, indeed some of the questions, I think I probably made the mistake that a few sub-questions are a little bit too difficult. They were bonus questions in the past offerings, and at this quarter, I thought that you have a team of 3 people, so maybe I can put them as regular points. But still, they are probably a little bit too difficult. They require some kind of tricks, as you probably noticed, some combinatorial tricks. Right. So, yeah. But I guess I checked the last homework. I think there's nothing like that. Like most of the questions are, and probably shouldn't require anything super special tricks about combinatorics. And I guess another thing is that if you want to take some bonus points, I guess there are other ways. For example, do some scribe notes, improve existing lectures. If you don't care about A+, I think the bonus point, the bonus points is always the same as the regular points in some sense. If you look at the grading policy, at least from your perspective, it's worth the same as the regular points. So from so basically the grading policy is that we first decide the cutoff before the bonus points, and then the bonus points can only make you have better later grade. Okay. Anyway, so yeah, I guess there are other very, very important, very nice feedbacks which I'm going to incorporate as well in the lecture. I'm not going to discuss all of those points just to save some time. So okay, so maybe let's get into the technical part. If there's no any other questions, other discussions. So I guess last Wednesday I was sick, and we skipped we asked you to watch the video online, and roughly speaking, what we did in the video is that we talk about this optimization, like non-convex optimization, and I think so. The main point there was that if you have the so-called property of low local minima, all local minima are global, then you can find global minima. Of course, there are technical things like there is so-called strict saddle point, which we discussed in the video, and there are other kind of like things that are a little bit subtle, but this is the main point. And so basically, you only have to show that this is true, and then you can find the global minimum of the non-convex function. And this line of research, from a broader kind of point of view, is successful. And in some sense, what I'm going to discuss next is another example of this. However, there are some kind of like special subtleties. So basically, what we showed last time is that this is really true globally. The statement all local minimum are global are basically, this is a true statement for the entire space. And today, what we're going to discuss is that you're only looking at a special part of the space. So in some sense, the function we are going to discuss this today is like look like something like this. You have some kind of like complex part about this function which you don't know how to characterize, but you identify a part where this is true. You look at a special region where all local minima are global, and there is actually a good global minimum there. So then you just only work in that region, that's kind of the connection to the previous lecture. There are other issues with this kind of approach. I guess we discussed a little bit in one of the outlining lecture. The limitation would be that you identify this region where everything is nice, the landscape is so nice, but is this the region you really care about, right? So if you really care about finding a global minimum of the training loss, then yes, this has to be the region because you find a global minimum of the training loss. But if you care about other properties, right, so like generalization performance, then it might be not the right region that you should focus on. So, but for today's lecture, we don't care about that, right? We just say, we are going to go through what this works, and then we talk about limitations, and in the future lectures, we're going to talk about ways to, in some sense, improve upon this, or kind of like fix the issues of this kind of approach. Okay, so that's a very rough, that's a kind of like a high-level overview. And also, by the way, if you haven't seen my notes or announcement on ad, so there are actually two videos that we asked to watch for making up the last lecture. So one of them is a full lecture, and the other one has like 15 minutes. So they are about this non-convex optimization, all local minima, global minima kind of phenomenon. And this does relate to one of the homework questions. The question itself is still, in some sense, self-contained, but I think it's useful for you to know the basic idea, even the basic proof ideas in those two videos, so that you kind of see better how do you do the homework question. Okay, so today let's talk about this the thing we are like about the special region thing. So, and this is also called neurotangent kernel approach. I guess the name doesn't really, so far just think of this as a placeholder. Like I'm gonna explain why this is called neurotangent kernel. So the basic idea is that you look at some special place around a neighborhood of your initialization, and you do some Taylor expansion. So Taylor expanding. And this works for any nonlinear function. So suppose you have a nonlinear, or even linear, but nonlinear would be the most interesting case, a nonlinear model f theta x. And then you do a Taylor expansion around initialization theta 0. So, and when you Taylor expand the model at the initialization, so your model is f theta x, you Taylor expand with respect to the parameters, but not input. So the input is fixed and the parameter is the variable. So theta 0 is the reference point. And then you look at the gradient with respect to theta, evaluate at the theta 0. This is the first order gradient times theta minus theta 0. So this is the first order Taylor expansion. And then you say you have some higher order terms, which we are going to ignore. So, and once you do this, you can define maybe this one. Let's call this g theta x. of course, it also depends on theta 0, but let's say theta is the variable, theta 0 is fixed. So this is a function of theta. So this is a linear function. So if you define this, then g theta x is a linear function in theta. Because where theta shows up, theta only shows up here, and it shows up linearly. And basically, you linearize your model. And you can also, I guess, define delta theta, which is the difference between theta and theta 0. I guess technically you should call this not really, this is a fine function because there is a constant term, right? A fine function in theta or in delta theta. You know, they are not too different. I guess just want to introduce this notation delta theta. And so I have theta 0, this reference point. This is a constant from this perspective, right? It's a constant that doesn't depend, that constant for fixed x, right? It doesn't change as you change theta. And in some sense, this is just not that important. And so sometimes for convenience, so not very important because it's a constant. And sometimes for convenience, you choose theta 0 such that f theta 0 x is equals to 0 for every x. How do you do it? So you do it. So if you really want to do this, you need to, for example, what you can do is you can design a network that you split your network into two parts, right? So maybe you have, suppose before you have a network, we have all of these connections, right? So and then for the second layer, maybe for some layers split into two halves, right? So you have something like this, and then something like this, and you do the same thing in these two halves, exactly the same thing in these two halves, and then you put +1 here and -1 here. So that they got canceled, so that you have still a somewhat random initialization, but the initialization has a functionality that the functionality of this initial model is 0. I'm not sure whether my drawing makes any sense. This is like a I see some confusion in your face, but this is supposed to be something simple. For example, let's say you have sum of linear models, sum of two-layer network, sum of AI times sigma of WI transpose X, I from 1 to I. Suppose this is a model. And what you can do is you can say you add it to minus AI sigma W transpose X. So you have two M neurons, and the WI is the same, and the AIs are paired, right? So then becomes 0, right? So if you have two M neurons and one part is the same as the other part in terms of W, and in terms of A, they are negation of each other, then you make it 0. And you still have relatively good randomness, right? You can still choose WI to be random, as long as WI, these are all WIs, and these are AIs. So anyway, this is a not super important point. And also, even you don't do this, you can still somewhat kind of get away from it because this f theta 0x is a constant. Okay, so basically from now on, we're going to assume this f theta 0x is 0 in most of the cases. So and if you think about this, right? So basically, this is saying that so y prime. Suppose you take y prime to be y minus this constant, which we are going to assume is 0. But so far, let's say this is for this equation, I think we can still think of it as generic. So then you get this is a linear function in theta transpose, right? So it's going to be grad theta f theta 0 x times delta theta, and this becomes a linear function in delta theta. So this, you can think of this as the parameter, and this, you can think of this as a feature map. So this is the same as the feature map phi of x that we discussed, for example, in CS229, right, when you have a kernel method. So, and while this is a feature map, this is something that doesn't depend on the parameter, right? So theta 0 is fixed already. So f theta 0 of x is really just a fixed function of x, right? So, so this is a fixed, let's call this of x, given the architecture and theta 0. But it's not, it doesn't depend on delta theta. So in some sense, it just becomes kernel method. And this so you can define, oops, what's going on here? So I guess if for simplicity, if you assume f theta 0, x is 0, then y and y prime are the same. So basically you're fitting a linear function to your target. And this becomes kernel method. You can define the kernel k x prime to be the inner product of features, right? The phi of x transpose phi of x prime, which is the inner product of these two gradients. Right. So and why this is called neurotangent kernel? The reason is that this is the tangent of the neural network. Right? It's the gradient of the neural network. I think then that's why it's called neurotangent kernel, because it's the feature is the gradient of the neural network. Anyway, the neurotangent kernel is just the name. So, okay, so and suppose we just use model. We just use g theta x instead of the original model. Then basically you just get kernel method, all linear model on top of the feature. Right, so and the loss function, so suppose you believe that theta is close to theta 0. So then you can also kind of intuitively say, okay, my original loss function, which is a function of the model output and y, probably is approximately close to my new loss function, right, which is g theta of x and y. And this is linear. And the whole thing is convex, because L is convex, right? A convex function composed with linear function is still convex, right? So this is when theta is very close to theta 0. And so basically the question, so the remaining thing is just really that, so how valid is this approximation? Right, because everything sounds nice, after we did this, like everything becomes super easy. But in what cases this can be valid? Go ahead.
The kernel, you define the inner product should be the big L2.
Yeah, so the inner product is just the typical inner product. You just take because these two are just vectors, right? So okay, so what's the dimensionality here? So gradient of this thing is in a dimension, let's say p, if theta is in Rp. So it has the same dimensionality as, okay, I guess it also depends on what f is. So let's suppose f is from some Rd to R, right? D is the dimension of x. Is the dimension of x. Then but the point is that the output is one-dimensional, and then you take the gradient with respect to theta, you get a p-dimensional vector, where p is the dimension of the theta. So the gradient with respect to theta has the same dimension as theta. That makes sense, right? So this is a p-dimensional vector, and you just take inner product of two vectors to define a feature. Make sense? Cool. Okay, so I guess to proceed, let's define two notations just for the simplicity. So let's define L hat f theta to be the empirical loss with the model f theta. This is just for formality so that we can write this easier in the, and f hat g theta is the loss with model x g theta. Okay, so the key idea is that, so in certain cases, this Taylor expansion makes sense, right? So I guess the Taylor expansion can make sense, can work for certain cases. Here we're gonna hide, they're gonna, for what cases it makes sense, can work. It's gonna be a big question, that we probably will discuss at the very end. But so far, let's see how does it work. So the way that it works is the following. So in the following sense. So how do you say it works, right? So you say that there exists a neighborhood of theta 0 such that in this neighborhood, so let's call this neighborhood B theta, theta 0, such that the several things happens. So one thing is that you have an accurate approximation in terms of function value. So the f theta is somewhat close to g theta f x, and L hat, as a result, L hat f theta is close to L hat g theta for every theta in this neighborhood, B theta 0. So that's something you want, which makes sense, right? So this is the point of Taylor expansion. You want to approximate our original function. And also you want that it suffices to optimize in B theta 0. Because if in this B theta 0 there's no good, maybe let me draw this again. So basically what we are saying is there is a neighborhood. Let's get B theta 0. And this neighborhood, first of all, you have, say, suppose your empirical loss is look like this. And maybe something else happening somewhere here else, we don't know. So first of all, if you do the quadratic approximation using the Taylor expansion around theta 0, let's say this is theta 0. You do a quadratic expansion, it looks something like this. It's very close. That's my drawing. So basically you can think this right one is g theta of x, and the black one is f theta of x. So the quadratic expansion is very close to the original expansion, the original function. And second, you want that it suffices to optimize here, right? Because if both the right and the black curve, even though they are close, if they are both very high, it doesn't make sense to zoom into this region, right? You should leave this region. But you can say that it suffices to optimize here in terms of in the following sense. So there exists an approximate global mean theta hat in B theta 0. So I'm using the superscript for this 0, which might be a good mistake, but let me consistently use that. I think in some other lectures, I use superscript for time. So that's why I keep using superscript for time. Anyway, so you want to have a theta hat such that it's global mean. And actually here you want that L hat G theta hat to be approximately 0. And this indicates that you are global mean, because 0 is the minimum. There's no way you can go below 0, you know. So if you are close to 0, it means you have to be close to global mean. And this also implies that L hat F theta hat is close to 0. Okay, so but with this two, we still don't really understand how do we optimize the black curve, right? So you also want to know that optimizing this loss L hat F theta is similar to optimizing L hat G theta. And not only this, but also, and does not leave B theta 0, right? Because if you leave B theta 0, then all bets are off, right? Your Taylor expansion breaks. So you have to say that when I optimize either the L hat F or the L hat G, I don't leave this region. So everything is confined to this region. And so this is how we make it work. Of course, you can ask, whether this is really reflecting the what happens in reality. The answer is no, not always. But so far, we are just trying to make this work under certain cases. So that we can appreciate why this, we have to improve this, right? So, and in some sense, 3 is kind of like a little bit like extension. So 3 to some extent follows from 1, 2, because if you have a global minimum in this region, right? So and the black and white are close, then why optimizing it? Optimizing it should converge to that global minimum, and you should stay in that region, right? To some extent, it follows 1, 2, but not exactly, technically. So, but still requires a formal proof. So what I'm saying is that, if you really just want something somewhat informal to think about the dependency, then probably you only have to first make sure 1 and 2 is happening. But if you really want everything, then you need to prove the 3. And 1, 2, 3, you can make this work. Can be all true in various settings, right? So with either over-parametrization or some particular scaling of the initialization. So if you play with the initialization, or you play with the width, and also you need small stochasticity, or even small or even 0 stochasticity. So if you play with the over-parametrization and scaling of the initialization, and also you insist that there's no stochasticity that make you go very far, because the stochasticity will let you leave the local neighborhood. So that's why you want small stochasticity. And so then you can achieve all of this. And how do you get small stochasticity? In a nutshell, you either need to get the small stochasticity, you need to either do small learning rate or full batch gradient descent. So in some sense, this is the limitation, right? So this is a limitation because you require this, and this is also a limitation because you have to play with it. You cannot just say, and what you really eventually get is probably not exactly matching what people do in practice. Okay, cool. So now let's see how do we do 1, 2, right? But still, like, regardless of all the limitations, still this is kind of an interesting approach, Like it's kind of surprising that such a region even exists. Even you think about 1 and 2, right? So you don't care about any limitations about it. It's still kind of interesting that there exists a such region that you can basically be close to a convex function, actually a quadratic function, if the loss is quadratic, right? And there's still a global minimum. They suggest that there's a lot of flexibilities in this landscape of networks, right? So when you have a lot of over-parametrizations and non-convexity, then somewhere you have to have a convex region, right? So that's basically what's saying, right? So in this landscape, globally, it's very non-convex, very complicated. But at some special places, in some neighborhood, you are really having a convex function, and that convex function has a global minimum, reaching area 0. So even this is still somewhat surprising. Right. So, okay, so now let's try to formalize 1 and 2. And then we talk about 3. So how do we do this? So let's introduce some notation. Let phi I to be the phi of xi, the features for the ith example, which is really this. And let's define this feature matrix to be phi n transpose. You put all the features in a row, and this is n by p, where p is the number of parameters. Okay, so now we can see that the loss function with respect to the linear model is just a linear regression problem, which you are probably familiar with. I'm taking quadratic loss or mean square loss. So this is just yi minus delta theta transpose times phi of xi. Recall that you have a basic linear model in delta theta and square. Right. So I guess maybe it's easier to write in the other way so that it's more consistent with the notation here. Transpose delta theta. So if you write in the matrix notation, this will be 1 over n times the 2 norm of y minus phi times delta theta, 2 norm square, where y vec is the concatenation of all the labels, which is in Rn. Right. So this just sounds very familiar with linear regression. It's exactly linear regression, where delta theta is your parameter, phi is your design matrix, or the feature matrix. So, and let's assume this is just for convenience, yi is on the order of 1, so that the 2 norm of y is on the order of square root n. So here's a lemma that kind of characterizes what is the I guess, so it's a lemma. This is in somewhat for 2. In some sense, you are trying to see that in what neighborhood you have a global minimum. So suppose p is bigger than n, you have more features and then more data points, and the rank of this feature matrix is equals to n, and the minimum singular value is equals to sigma larger than 0. Then let be norm solution to y hat to this. Right, so you want to fit phi delta theta to y vec, and you want to understand what is the nearest global minimum, right? So delta theta this is the nearest global minimum. This is the nearest global mean in some sense, right? Because if you fit it, you are achieving the global mean, and you want delta theta hat to be the smallest, so that means you are looking for the nearest one. And if you're looking for the nearest one, then you can have a bound on the nearest global minimum, where the bound is something like this. Square root n over sigma. So the bound itself so far is not that interpretable, but the point here is that if you take the ball, this means that if you take the ball b theta 0 to have this radius, right, to be all the theta such that is equals theta 0 plus delta theta, such that delta theta 2 norm is less than of square root n sigma over sigma, then this ball, this b theta will contain a global minimum. Contains a global mean. Okay, so this is characterizing how large the ball needs to be, or how large the region needs to be, so you can contain a global mean. And the number here, so far the number is not interpretable. I'm going to compare it with some other things, because by itself, how large the region. If you just care about 2, then you can just take the region to be as large as possible. You have to compare it with something else. And the proof is also pretty easy. This is really just a simple trivial thing, like you say, you can write delta theta hat to be, because you are the minimum norm solution is the pseudo inverse of phi times y vac, and there's some, I guess this is not extremely obvious, but you can invoke, this is some relatively basic properties of the pseudo inverse. You know that the operator norm of the pseudo inverse is less than the minimum singular value of phi. Actually, these are, I think they are exactly the same. So, and this is equals to 1 over sigma. And then you know that you have a bound on delta theta 2 norm by using the operator norm of the pseudo inverse of phi times the 2 norm of y vac. So this becomes 1 over sigma times square root. That's it. I guess I don't even need the big O. I don't know why I have the big O. Sorry. Just for me, like, it's always safe to have big O, so it's just part of my brain. You cannot work without big O anyway. But here you don't need anything, any constant. So, I guess there's a. I think I need a big O because I'm only assuming that y is on the order of square root n. Sorry. So because here I'm only assuming this is y is less than O square root n. So that's why I need a big O. But anyway, the constant doesn't matter here. You get the point, I guess. So, okay. So, any questions so far? So, and now let's see whether this region is, whether it's too big or too small, right? It sounds somewhat big because n is there, right? But actually, you'll see that the region is not that big because the sigma could be made very big in some sense. Or there's some relative kind of things which you have to compare it with something else, right? So because you have to compare this with how good you have an approximation in the region. So the next one is for, so the lemma. So this is for 1 in some sense. So suppose this is beta Lipschitz. Suppose this gradient of the network is Lipschitz in theta, in the sense that for every x, for every theta and theta prime, you have this So I think this is 0. Because we always only care about the gradient at theta 0, evaluate at theta 0. Wait, sorry, my bad. this is you viewed it. Sorry, my bad. Okay, so this is a so here what I'm writing here. This is a function of theta because I evaluate at some arbitrary theta. Let's say I evaluate. So I want this as a function of theta to be Lipschitz in theta. So that means that if you choose two different places where either theta or theta prime, the differences between them in L2 norm, I have to use L2 norm here because they are vectors. And you want to say that L2 norm is bounded by the differences in the theta space. So if you have this, then we know that f theta x minus g theta x, your approximation is less than big O beta times the difference the delta theta, 2 norm square. Right? Because the difference between these two is basically in some sense depends on how far you are away from the reference point. Right? If at the reference point it should be exactly the same, and if you're a little bit more away from the reference point, then you're going to incur some loss, and the loss is something on a second order, right? That's also intuitive. So and the important thing is that so for every theta in the b theta 0 that we just defined, we have that f theta x minus g theta x is less than beta n squared over sigma squared. And that's just by plugging in the definition of b theta 0. The b theta 0 has this radius, square root n over sigma, and you plug it into this here. Then you get, so you plug in this here. You get that in this neighborhood, you have some bound on how good your approximation is. So, oh, sorry, this beta n, my bad. It's just a copy pasting error. Okay. Yeah, beta n squared. Okay, so far this bounds. So I saw a question. By the way, you can feel free to unmute, but I can read the question now. So how do we define phi superscript plus? Oh, this is the, so what is this phi plus? This is the pseudo inverse of phi. I think this is called, there's actually, this is the most common definition of pseudo inverse of phi. I guess you can roughly think of as the inverse of phi, with some small caveat. Yeah, yes, more Penrose pseudo inverse. Thanks for the comments in the chat. This is, I think this is supposed to be taught in the linear algebra course. Maybe, I don't know. Like, I'm not sure what I can say about it. What you know about it is that, at least in this case, I think maybe just for the sake of simplicity, just think of the pseudo inverse as the inverse, so if you are not super familiar with it. And then you can verify this is a good solution to this equation, right? Because if you multiply pseudo inverse, you get this pseudo inverse cancels with phi, and you get delta theta. So you plug in this delta theta to this equation, you can cancel phi and phi pseudo inverse, and you get y vec. That's how you get the how do you verify this is a solution to the equation? Okay, so and also I think another useful thing to know is that the pseudo inverse has exactly the same. It has the inverse of the spectrum of the original one, right? So suppose the phi has singular value sigma 1 up to sigma k, and then phi pseudo inverse has singular value 1 over sigma 1 up to 1 over sigma k. So, and this, if all these sigmas are positive, right, you ignore the zero singular values, then this is exactly true. So the singular values are just inverted. Okay, cool. So I hope that answers the question. Okay, going back to the second lemma for number 1. So this is saying that, in this neighborhood, how good your approximation is, right? So we got this, like number. So I'm going to explain this number. That's the important thing, right? So how small is this, right? If this is small, that's great. If this is big, that's a problem. So, but maybe just let me just say the proof for this lemma. The proof for the lemma is kind of like basically just follows the basic fact that from the fact that if you have h, theta satisfies gradient of h theta is Lipschitz, and this gradient of theta is Lipschitz is basically equivalent to the Hessian in operator norm is bounded by beta. If everything is differentiable, then you can bound the quality of the Taylor expansion. So you can say that g theta minus g theta h theta 0 minus gradient h theta 0 theta 0. This is bounded by O of beta theta minus theta 0 2 norm square. And this h theta will be just f theta x. In our case, if you take h theta to be f theta x, then you get the lemma above. So the point is that the approximation error is second order in the delta theta, in the difference between your point and the reference point. So okay, and there's a small remark. Another small remark is that if the f theta involves ReLU, then nabla f theta is not even continuous. So it cannot be Lipschitz everywhere. And this requires some special fix. So it requires special fixes. The fixes is not that surprising, just because even though it's not continuous everywhere, it's still continuous almost everywhere. So basically it's kind of close to be Lipschitz. And in some sense, L f theta x is still, like, if you look at the average over data points, then you still have some Lipschitzness. But I think let's not discuss that. It's a little bit kind of like a low-level details, which is not important. We can just assume we are dealing with not ReLU. We are dealing with something like sigmoid. Then there's no such issue. Okay, cool. So now let's go back to the main thing, right? So the main thing is that whether this is a good bound, right? So like you say that you have found this b theta 0, and you have shown that in this b theta 0 you have such a good approximation error. So the important fact is that what is this beta n sigma square? Is this small or big? And the important thing is that, so the interesting thing is that this thing is not scaling invariant. So n is something you cannot change, right? But beta over sigma is not scaling invariant. So what does that mean? That's I think you can interpret this in some way. So but in some sense, like beta, basically I think the easiest way to think about it is that you have a square in below, right? You have beta, the beta on top. So somehow you can play with the scaling so to make this going to 0. So there are two cases. Actually, there are more than two cases, but I'm going to discuss two cases. These are in different papers, but I'm going to unify them in the following way. So there are two cases where beta over sigma square can go to 0. So the first way is that you can re-parametrize with a scalar. And this is in Chizakt and Bach. I think this is 19, and the paper is called Lazy Tuning of Neural Networks, something like that. So I guess the paper title suggests that they're saying that this is a lazy way of tuning networks. It's not really the final way you should believe in. But nevertheless, the paper is very nice. So And what they do is the following. So they say that they let your f theta x, your parametrization, to be the following. You take alpha times, let's say, f theta bar x. So, and this, let's make this a fixed. This is, let's say, this is a standard neural network, a standard neural net, and fixed. Fixed in the sense that you don't change the architecture, right? You don't let you just take whatever standard neural network, with any finite width, with fixed width, and depth, so on and so forth, right? Something that you don't change, at least for this perspective, and you only change alpha, right? So for every alpha you define perfect is a valid network. It's just you have a different scaling in front of it, right? So for every alpha you got a neural network. And then let's see how does everything change as you change alpha. And also you fix initialization, scheme theta 0. And then let's consider, let's say sigma bar is the sigma mean of the base network. Let's say the base network is the f bar theta, right? So it's the sigma mean of this base one. Right, this is the right, and let's beta bar be the Lipschitzness, beta bar be the Lipschitzness, also of the base one. So you can think of sigma bar and beta bar are not changing as you change alpha, right? So, and now let's see how does the alpha change the final sigma and beta of your final network, right? So then, so sigma is equals to alpha sigma bar, because once you have considered f theta, you multiply as alpha, right? So all the features, right, like the gradient becomes alpha times bigger, and everything becomes alpha times bigger, right? So, right, this is just because when you take the gradient with respect to, so this is just because of chain rule, right? So if you take gradient with respect to theta of the f, it's the same as alpha times the gradient of theta with respect to the gradient of f bar with respect to theta, right? So you have a chain rule. So everything got scaled, and beta also got scaled by alpha, just because the gradient got scaled for the same reason. And then you can see that you get for free of some factor about alpha in this equation. So beta over sigma squared becomes beta bar over sigma bar squared times 1 over alpha. And this can go to 0 as alpha goes to infinity. So basically they're saying that whatever network you take, whatever initialization, right? So as long as your sigma bar and beta bar, they are reasonable and they are not 0 or something like that, right? So as long as sigma bar is not 0, so you have some beta bar over sigma bar square. That might be bad, but you can always rescale, reparametrize it with a constant in front of it, so that this key quantity beta sigma square becomes going to 0. And if this goes to 0, what does it mean? It means that your approximation becomes better and better, right? So, and until some point, if you change your alpha large enough, you make this approximation super good, right? So, and the neighborhood, so basically you found the neighborhood such that in that neighborhood, your approximation is very good if you take alpha to be big.
When you take alpha to be big, then would then like the laws would be made?
No, the laws wouldn't change, right? Because the laws, that's a good question, right? So laws, what is the laws? The laws is something composed with the composed on top of with the network, right? So the loss is L of, for example, alpha f bar theta x y, right? So first of all, at the initialization, we always try to make the initialization zero. The output at the initialization 0, so that wouldn't change. And second, even though seemingly this whole thing is big, sure, that's true, but we show that you have a global minimum, where in this neighborhood you have a global minimum. I'm not sure whether that makes sense. So in some sense, I think, okay, let me try to draw a figure to answer this question. So the question is that, what happens when alpha is big, it sounds like function value becomes big, right? So that's true, but I think I think what happens is that, for example, suppose you have not sure. So how do I visualize this? So I think your loss will be, so if you stretch alpha, your loss will be sharper. Your loss will, so if you look at everything, you look at dependency on alpha, right? So if you make alpha bigger, you make this neighborhood smaller, right? So you make the neighborhood smaller, so you're gonna get something like this, very sharp in the neighborhood. And however, so if alpha is bigger, actually you can find even something that is very close by to make the, so like you have to even move even less from initialization. Just because if you do a little bit of work, then you actually already kind of like already fit the data. I'm not sure whether that makes sense. So okay, so there's always one thing which is useful, which is like the f theta 0x. This is 0. So basically, you always start with this, right? Where you don't have any scale, right? So this is just literally 0. And if alpha is big, then this is still 0, right? But when alpha is big, you are more sensitive to theta, right? So that's why if you change a little bit, then you can already fit your data. So you only have to change very, very little from the theta 0 to fit your data. And when you change very little, then your approximation is very good in that neighborhood. I'm not sure whether that makes some sense. But maybe you can discuss. It's a little bit counterintuitive. I agree, but right. It's just it really, because the only thing that happens here is like how does this beta and sigma relative, the relative difference between beta and sigma, how does that depend on alpha, right? So so in some sense, if you have larger alpha, you need to have smaller neighborhood, but your but the approximation error scales faster because your function is kind of much kind of like more non-smooth, right? So like your function becomes like sharper. So but actually the neighborhood shrinks faster than the sharpness grows. So that's why it's working. Yeah. I hope that somewhat answers the question, right? Yeah, but this is kind of somewhat kind of confusing. And this is another case where we can also see this. So the other case is if you over-parametrize. So here, let's say, suppose this is actually the original first few papers that like which invents the NTK approach take. So so basically what you do is you say you have a model y hat, which is equals to 1 over square root m times sum of ai sigma wi transpose x. This is a two-layer network with m neurons, and I'm scaling this just in some sense mostly for convenience, because whatever scale you do, you can also change other scales to compensate. And the convenience comes from that if I choose everything on an order of 1, then this will output something on the order of 1, which we will see. So, but maybe let's discuss that in a moment after I introduce the notation. So I'm gonna have this matrix W, which contains all the rows, and W is in M by D. and sigma is ReLU here. I guess ReLU, let's say is, maybe let's not say sigma is ReLU. Sigma is something like it's 1 Lipschitz, and it has second order derivative. So actually, yeah. So you wouldn't see how those come into play explicitly. They're not super important. And what is initialization? Those AI 0. So actually AI is initialized to be +1 -1 initially, and not optimized at all. So they are not even parameters, technically speaking. And WIs are parameters. WI0 is initialized from Gaussian, a d-dimensional Gaussian with spherical covariance. And let's say X has the norm. So the norm of X is on the order of 1. It's on the order of 1. This is just for convenience, so that we have a fixed scaling. And let's say theta. So the parameter theta is really just a vector version. D times M is just really a vectorized version of W. So vectorized version of W. Okay. So we'll assume M goes to infinity. Like so M is eventually technically Pauli N and D. So N and D are considered to be fixed, and M is something that will becomes bigger and bigger, and that's the power. So like everything comes from the scaling of M. So I guess just to explain why we want to have this 1 over square root M and the initialization scale like this. So scaling, and I think the reason, at least one reason, is that if you look at this, so sigma Wi 0 transpose X, this is on the order of 1. Because Wi is a spherical Gaussian and X has norm 1, a spherical Gaussian times a norm 1 thing will have expectation, like will roughly be on the order of 1. And then you take some ReLU or kind of something like ReLU sigmoid, then you're going to be on the order of 1. And then the sum of this will be on the order of square root M, right? Because you have M of these things that are somewhat +1 -1, and you, because AI is +1 -1, so you cancel them in some sense, and then you get square root M. So, and that means f theta 0x is on the order of 1, because you'd have another 1 over square root M in front. So that's one of the reasons why you choose this scaling. Okay, so initially our output is on the order of 1, and now let's see how does the sigma and beta depends on all of these quantities. So we hope that this key quantity beta over sigma square to go to 0 as M goes to infinity. So so let's first look at the sigma. Sigma is the sigma mean of this feature matrix phi, and you can, this is also the same as the sigma mean of this phi transpose. This is just equality because phi transpose, the spectrum is just the squared of the spectrum of phi. And what is phi transpose? Phi transpose is basically this empirical kernel matrix, right? The ij's entry is just the inner product between two features of two examples. Right, so, and let's look at what the scaling of this phi transpose. So to do that, you have to look at what's the gradient. So let's look at the gradient. So f theta if you look at the derivative of the output with respect to each of these wi, then you can use chain rule and then you can get something like this times x. So this is the gradient of every neuron wi, every vector wi. And that means that if you look at the gradient, the entire gradient, all the gradient of all the vectors, if you look at the norm, then it's 1 over m times the sum over m wi transpose x times x 2 norm square, which is 1 over m times the 2 norm of x squared times and what is this? It's kind of hard to know exactly what is this, but I think you mostly care about what's the dependency on m, right? So what's the dependency on m? Then this, as m goes to infinity by concentration, so yeah, as m goes to infinity, this is really just converging to expectation because this is an empirical sum. There's a 1 over m here, right? So sigma prime w transpose x square, where w is from spherical Gaussian, times the 2 norm of x squared, which is a constant, which is 1 basically, right? So and this whole thing will not depend on, this whole thing will be something like O of 1. So I guess, to see it's O of 1, maybe it's somewhat tricky, but at least you know that this is not depending on m. So m is not in this equation. So basically this is saying that every quantity here, as m goes to infinity, is the norm of this is on all of 1. Doesn't change as m goes to infinity. And also you can do the same thing for the inner product of two example. And the same thing happens that if you look at the inner product is something like this. I transpose. So this is, I think technically there should be a 0 here because this is the initialization. X prime. And as m goes to infinity, so as m goes to infinity, by concentration, this is concentrated around the expectation of it. The expectation is something like sigma prime wi transpose x, sigma prime wi transpose x. As I can write following w transpose x, sigma prime w transpose x prime times x in the product with x prime, where w is from spherical Gaussian. Right. Okay, so again, this does not depend on m. Okay, so which means that, so basically this is saying that this entire matrix phi transpose, goes to some kind of a constant matrix. Constant matrix as m goes to infinity. And I think this matrix, sometimes people call it K infinity. And this is the neural tangent kernel. This is the neural tangent kernel with m is equals to infinity. Okay, so this is a fixed matrix, and you can show that this is a matrix that is like at least has is a full rank. So I'm gonna skip this part. So it can be shown that this K infinity is full rank. So, and let's take sigma mean to be the sigma mean of K infinity. which is larger than 0. Then basically you can show that the phi transpose for the sigma mean of phi transpose phi. This is, larger than, for example, up half times sigma mean if M is sufficiently big. Just because, phi transpose is converging to the constant matrix K infinity. So if M is sufficiently big, then the eigenvalue should also converge. This part, again, is not like I didn't do it exactly rigorously, but you can expect that when you converge to some matrix, your eigenvalue should also, your spectrum should also converge to that matrix. Okay, so with all of this, right? So basically, this is saying that your sigma is not. This is our sigma, right? The sigma is not changing in some sense as M goes to infinity. But let's see what beta changes. So now, how beta changes as M goes to infinity. We'll show that the beta will goes to 0 as M goes to infinity, so that beta over sigma square, the key quantity will goes to 0. And let's see how much time I have. Okay, so now what we do is that, so we want to look at the Lipschitzness of beta, which means that you care about these two things, the difference between these two things. And we have computed, what the gradient is. The gradient, both of these are matrices, because theta is a matrix, right? So, and the gradient of each column or each row is something like this, right? So this is really a matrix with entries times x, where I is from 1 to m, right? So you have each of these is a gradient. So that's why if you look at the norm between these two, if you look at the Euclidean norm, then it's the sum of the norms of each of the components. So you get 1 over m, which is come from this 1 over squared m. And then you look at the norm of each of these components. This is a scalar, this is a vector. So you get x2 norm times the scalar sigma prime x minus sigma prime wi prime transpose x squared. Right. So and then suppose you want to get, let's try to get rid of this sigma prime. So let's say this is less than 1 over m times just without the sigma prime. And this is you're assuming that sigma prime is sigma prime is 1 Lipschitz or 1 Lipschitz. I guess let's pay a big O here. And then, of course, this doesn't work for ReLU. As I said, for ReLU, we have to fix it in some way. Okay, so, and then you say that this is, you get rid of the x again, so m times sum over m. I guess the norm of x is 1, as we claimed. So, and this one, we just use Cauchy-Schwarz, let's say, wi minus wi prime, 2 norm square times x2 norm square. That's this part. And x2 norm square is also 1, so we can just do this. And then this is 1 over m times the distance between theta and theta prime. in Euclidean distance. So this is saying that the Lipschitzness is 1 over m. Oh, I guess the Lipschitzness is 1 over square root m because we didn't take the square root, right? So x to norm is less than 1 over square root m. 2. So beta is 1 over square root m. And now if we look at this key quantity, beta over sigma square, then this is equals to 1 over square root m over sigma. Sigma is something like sigma bar square. So, sorry, sigma is this something that doesn't depend on m, right? So sigma mean square, right? So this will go to 0 as m goes to infinity. So here I think the radius you need is always the same because sigma is always the same. But your function becomes more and more smooth. Your gradient becomes more and more Lipschitz as you have more and more neurons. So that's why eventually, as you have more neurons, you can get into this regime. Let's see. Okay, so I guess let me take the next 10 minutes to discuss the outline of the next steps. So any questions so far? So now, suppose let's try to establish 3. So recall that 3 is about optimizing G and optimizing over F are similar, right? So you can basically do 2 things, right? So like all the analysis, there are a lot of different ways to analyze this, and all the analysis kind of like probably you can think of as 2 steps implicitly, even though the first step probably don't have to write in the paper, but I'm pretty sure many people do that when they derive the analysis. So your first step, it sounds reasonable to say that you first analyze optimization of L hat G theta. And the second step is that you somehow analyze optimization of L hat F theta by somewhat reusing proofs in A in some way. Of course, you cannot reuse exactly, but you can probably reuse most of the ideas, right? So, and your intuition is that these 2 things are similar, so somehow you can reuse the proof to do the actual optimization for the neural network F theta, right? So, and there are 2 ways to do for A. I think essentially you can say 2 ways. Maybe there's possibility that I missed some of the existing papers, but roughly speaking, there are 2 ways for A, and therefore there are 2 ways for B in some sense. So the first way, let's say I, is that you leverage the strong convexity of this L hat G theta. And then show exponential convergence. I have to say that this, the definition of strong convexity, I'm not sure whether I have really given it in this course. This is a stronger notion of convexity. If you haven't heard of it, you probably don't, it's not super essential for this course. But if you have heard of it, you know what kind of things I'm talking about. Because this analyzing A, this is analyzing how to optimize a convex function. It does require a little bit optimization background. At least like on a conceptual level, you can imagine there are many different ways to analyze optimizations for regression. So strong convexity is the stronger version of convexity, and you can somewhat use that to get the very fast convergence rate. Exponential means every time you decay the error by a constant factor, so that you get exponential decay of the errors. And another way to do this is that you don't use the strong convexity, because sometimes you actually don't have the strong convexity in certain cases. So you don't use the strong convexity, but only use the smoothness. And smoothness means that you have a bounded second order derivative. And again, if you have taken some courses about optimization, then this would make a lot of sense probably, because there are different ways to analyze optimization. Sometimes you only have smoothness, you have a different kind of analysis. And based on these two approaches, you can get two different proofs for B as well. And we're only going to talk about A. So we only talk about A. Talk about I, the first approach. And for this approach, there is no prior knowledge is required. You probably wouldn't understand exactly what I'm saying about this conceptual thing, but the actual proof doesn't require prior knowledge. And it's actually also pretty intuitive by itself as well. So I think we're going to talk about the approach, the concrete analysis next week, next lecture. But before ending this lecture, let me make another remark, which I think is useful. And in some sense, it's useful for the second approach more, but it's also useful for the first approach. So this is an interesting observation, or maybe intuition, you can say. So, and particularly useful for 2. So this is at any theta t. So suppose you take this Taylor expansion, with reference point theta t. So now we are not taking Taylor expansion at theta 0, we're taking Taylor expansion at theta t. You can define this g t theta x is a function of theta, and it Taylor expand at theta t. So the reference point is theta t, and you have gradient f theta t x times theta minus theta t. So this is the linear function. And then you can consider nabla L f theta at theta t, right? So this is the gradient that this is the gradient you are taking, because what you really care about is optimizing f, right? So this is the gradient you are taking, but actually it's the same as the gradient of this Taylor expansion at the same point theta t. So these two things, yes, there's 2t here. This is theta t, and this t is indicating that this is also Taylor expansion at the reference point theta t. So why this is the case, I guess, if you want, you can take the derivative, you can verify it, but fundamentally, this is actually, it's really just saying that f theta t, f theta and g theta t agree up to first order I theta t. This is by Taylor expansion. If they agree up to first order theta t, and then anything that's like L, so this implies L of f theta and L of G theta T also agree up to first order at theta T. So that's why. So what does this really mean? This really means that gradient descent on f on this function or maybe technically on L hat f theta, right? You are taking gradient only with respect to the f. This is the same as taking online gradient descent on, I guess I haven't defined online gradient descent, but let me define that in a moment after I write down on a sequence of changing objective. LG theta 0 up to LG theta T. So what does online gradient descent really mean? It just really means that every time you take the gradient of the new function, you have a sequence of functions, and every time you get a new function and you take the gradient of that function, you take one step. So that's online gradient descent. So basically you are saying that taking gradient descent on this fixed function L hat is the same as taking gradients updates with respect to a sequence of changing functions. And this is actually how the second approach really works. So this means that you can use online learning approach. I guess in this quarter, I'm not planning to talk about online learning, but online learning is trying to deal with the case where you have a sequence of changing functions, right? So you are not optimizing a single function. You have a changing, for example, changing distribution or changing environment or changing loss function whatsoever. So there's a rich literature on how do you analyze optimization when you have a sequence of changing loss functions, and this is exactly how what this is about, right? You're having a sequence of changing loss functions, and if you can analyze that, you can analyze the original cases. Now here there are also like spectral structures about these loss functions because they are all somewhat similar to each other, right? So they are all Taylor expansions with respect to reference points that are in a small region. So you can also leverage additional information about that. So yeah, so this is chapter 10 in the lecture notes, but I think in this quarter, I just don't think we have time to go there. Okay, I think I'm already 5 minutes late. And next lecture, we are going to talk about the approach 1, which is more self-contained and also kind of cleaner to some extent. Okay, maybe just a last comment. I think there are many different neurotangent kernel papers. I'm not super comprehensive, but I think most of them basically is a combination of these several things, right? So one thing is that you have to optimize this, establish this third step of optimization, and you have two large ways, and maybe some even subtle differences and underlying differences. And also you have to establish the first two properties, and those are properties not about optimization, they're about your parametrization of your function class or initialization, right? So there you can also have a bunch of different flexibilities. You can change the reference, the scaling, you can change the width, you can do many different things. Or you can even change, for example, the architecture in certain cases to make it more efficient or less efficient in certain cases. Yeah, so I don't want to have a very comprehensive discussion of this NTK just because there are so many limitations, but I think it's a useful thing to know given that there are so many works in it, and there are indeed some nice ideas there. Okay, cool. So I guess I'll continue next Wednesday.